Hello everyone, I'm Alif bin Abdul Qayyum and my co-author is ANM Nafiz Abeer. Both of us are PhD students in Department of Electrical and Computer Engineering at Texas A&M University, College Station, Texas. I'm going to present our work solving Kuramoto Oscillator model using physics-informed neural network. This work has been accepted to the third Muslims in ML workshop, co-located with NeurIPS' 2024. Kuramoto model is actually a way of representation of collective dynamics, for example, neurobiological systems. This has recently gained attention in optimal experimental design. The origin of uncertainty in a Kuramoto model or collective dynamics comes from the unknown interaction strengths between different oscillators of a Kuramoto model. And as the objective here is to minimize the uncertainty, to quantify the uncertainty first, we need to solve numerous number of different Kuramoto oscillator models. However, solving numerous Kuramoto oscillator models might be challenging due to computational resources and also computational time. We evaluate physics-informed neural network as a fast solver to Kuramoto model, which can be used as an alternative to slow numerical methods. So Kuramoto model or Kuramoto oscillator network is actually a network of different number of oscillators which are coupled through either same or various coupling coefficient values, and the behavior of the overall Kuramoto model is governed by a bunch of coupled differential equations. The reason behind coupled differential equation is each of those differential equations are interrelated through the coupling coefficients, which here is shown as a subscript I, j. The higher the coupling coefficient, the more the different oscillators are connected to each other and they behave in a synchronized manner. The lower the coupling coefficient, the less connected the different oscillators are, and they tend to behave in an unsynchronized manner. We use physics-informed neural network, abbreviated as PINN, to solve a Kuramoto model. So basically, we are trying to solve a bunch of coupled differential equations through physics-informed neural networks. PINNs have recently gained attention for solving differential equations. So we use a feed-forward neural network model here. Capital W represents the parameters of the neural network. We have the boundary conditions or the initial angular positions of the different oscillators represented as theta superscript 0. So when we train our PINN, what we do is we try to minimize a combination of two different losses. LB is the boundary loss, where the loss comes from the evaluation of the PINN network at the initial time point, and the residual loss LR, where we evaluate the PINN model at other time points, and we try to minimize the residual values. And the residual value is described as the showed equation here. And the overall objective is to minimize the weighted average of the boundary loss and the residual loss. Here are experimental results for two different Kuramoto models. The first row shows the actual solution of a Kuramoto model where the coupling coefficient is 0.1, and the PINN solution, you can see that it can capture the actual angular values at different time points, where we have a lower value coupling coefficient for the Kuramoto model. However, when the Kuramoto model has a high coupling coefficient, that means it tends to behave in a synchronized manner. The PINN model fails to capture the actual solution. Then we did a bunch of different experiments where our goal was to only minimize the residual loss, and we didn't have access to the initial conditions or the initial angular values of the different oscillators. Here, the objective was to see that whether we have a Kuramoto model that our PINN model is trying to solve, and if that PINN model, if that Kuramoto model has a locking frequency, whether PINN can actually learn that locking frequency without even trying to learn the initial conditions. And as you can see that it can actually capture the locking frequency or the instantaneous frequency of different oscillators. So you can see that at initial time points, even though the PINN does not capture the actual instantaneous frequencies, however, eventually it actually predicts the actual instantaneous frequency for all the different oscillators. So the key takeaways we can say is the objective here was twofold. First, to see whether PINN can actually solve a Kuramoto model with all the initial conditions. It can when the Kuramoto coupling coefficient is smaller. However, it cannot when the coupling coefficient was higher. And if there is a locking frequency for the Kuramoto model, that is, it tends to behave in a synchronized manner, the PINN can actually learn the locking frequency or the instantaneous frequency of different oscillators, even if we don't train the PINN with the initial conditions. So thank you, everyone. This is the contact point for both of the authors. Please feel free to reach any one of us if you have any questions.